Okay, let's talk about direct current circuits. That's what DC stands for, is direct current. And before I do it, let's take a look at a DC circuit. Here I have electric cells. Now these are called electric cells, but what do we call them in everyday language? We call them batteries. But this is really one cell, and here's another cell, and when you put them together like this, we call it a battery of cells. But in our everyday language, we just kind of shorten it, just calling it a battery, and then now this has become just a battery. So, and that's fine. I'm going to use that language. I'm going to call this a battery instead of a cell. But you might want to know, in case they ask you something on a state standards test, hey, this is an electric cell. Okay, put it together like that, and now you've got a battery. So, and then what I'm going to do is I'm going to take this. Now I have to hold it in my hand because I have to hold the batteries together. And then I've got right here, let me find a better one. Here's a good one. This, it looks like it might be burned out. Let's see. No, it still works. This is a Christmas tree light. Not the diode kind. This is kind of the old-fashioned kind. And notice that if I hook it up to the batteries correctly, it gives off light. See the light? And but if I do this, there's no light. Now, I'm going to approach DC circuits from the point of view of energy. We're going to talk about current and voltage. We're going to talk about current. We're going to talk about voltage. We're going to talk about resistance. We're going to talk about power for DC circuits today. But here's what's going on. Now that's a change, isn't it, in the environment. This little light bulb is changing the environment. It's giving off light into the environment. Well, what is required if you're going to make a change to the environment? Energy. So this involves energy. So there's energy stored in these electric cells. And what we're going to do, so here it's stored up. It's called chemical potential energy. In chemistry, you might learn about that. I mean, you might learn about electrochemistry. It's a really important area in science. Now, if I only have one electric cell, and then I do this, you can kind of see, I don't know if you can see on the camera, can you see it glowing a little bit? There we go. Turn it off, turn it on. But if I put two of them, there's more energy available, so it burns brighter. That's cool. So, we're going to talk about this. Now, I could do this. I could try to draw it like this. Okay, here's the plus side of the battery. And I'll go ahead and put two of them. So here's my two batteries, and then here's my wire, and here's my little here's my little filaments inside, and it's giving off light. Okay, so this is called an electric circuit. Now, what do we mean by a circuit? A circuit means that there is a closed path for the electricity to follow. See it? The electricity is going to follow this closed path. Now, batteries, but you see, this is kind of awkward. I don't want to draw this like this. We have symbols that we use to represent batteries, and symbols to represent things like light bulbs or motors or toasters or whatever's using the energy that's in the electricity. We call those resistors. Resistors are elements within a circuit that use the energy that's available. So we have a symbol for this. It looks like that. These are like two electric cells put together. And this will be the plus side, and this will be the minus side, which I'll explain in a minute. Now, here's the light bulb. But remember, it doesn't have to be a light bulb. It can be anything that the electricity is going to be used to have an effect on. Okay? And, hey, he needs to pay attention. Turn around. Sit over there and face forward, please. You're not allowed to sleep. Okay, this, we use a zigzaggy symbol. And we call it a resistor. I'll put an R there for resistor. Now this battery, we're going to discuss it here in just a minute, but it has what's called voltage, and I haven't defined it yet. I will define it in a minute. I'm going to call it delta V. Now let's take a look at a little chunk of wire right here. I'm going to blow it up. So here's a little tiny chunk of wire. So we're just looking, the wire goes up and down like this. Now, what do you think this wire right here is made out of? What is this stuff? It's copper. Any metal, by the way, will conduct electricity. But copper is a really good metal for conducting electricity. It's very easy for electricity to flow through it. Copper is very flexible, it's soft, and yet it's strong. It won't break, it's not brittle. It's relatively cheap. I mean, it's not the cheapest metal in the world, like iron or steel or aluminum. And they do make wires out of aluminum. Very rarely do you see wires made out of steel, because the resistance is pretty high in steel. And it's also doesn't, it's not as flexible. But copper's great. Copper's kind of the optimal metal to conduct electricity, so that's why we use it. Now, all metals have this property. They have atoms in them, right? And if you remember, atoms are made out of what kind of particles? Well, in the nucleus of the atoms, you have protons and neutrons. And buzzing around the nucleus of the atom, we have electrons. Now these subatomic particles apply forces to each other. Okay, we call them electric forces. And now, this is what we observe about nature. Okay, when you pull your socks out of the dryer and you get that static electric cling, we observe that, and that's what's happening here. It's the force of attraction and repulsion between protons and electrons that's doing that. And so this is just the way our universe works. Now, if you have an object where most atoms have exactly the same number of protons and electrons, right? And so you learn that in chemistry. And so they don't have a net charge. But if if your socks, as they tumble around in the dryer, they either collect more, or I don't know if they collect more electrons or if they have too few electrons, but there's an imbalance between the number of protons and electrons they have, so they get a static electric charge on it. So if something has more positive charge than negative charge, we say it has a net positive charge. So I draw a bunch of little plus signs on there. Now, what if I put another object with positive charge near it? What are we going to observe? Well, they are going to repel each other. Like charges repel. If I have an object that has more negative charge than positive on it, a surplus of electrons, then these will also repel. But what happens if I've got positive charge over here and negative charge over here? What will these objects do? They will attract each other. So like charges repel, unlike charges attract. Now, in going back to my copper wire, here's what happens. I've got electrons in here and protons. Wires have exactly the same number of protons and electrons in them. They are electrically neutral. But metals don't hold on to their outside electrons. What do we call the outside electrons in an atom? Do you remember from chemistry? The valence electrons are not held on very tightly at all. In fact, in a metal, the atoms share their valence electrons. The valence electrons just move around the metal. So here's a valence electron. So I'm going to draw the valence electrons, just a few of them. Now what happens in this wire is this. The battery on the negative side, it forces electrons into the wire here. And it attracts electrons over here. So what happens is this, if I look over here and if I follow this around, the electrons push each other through this electric repulsive force. They push each other down the wire. And you get a flow of the valence electrons. Now there's no net charge in there. Remember that the protons are there. So you have just as many protons as electrons. But the valence electrons are free to move. And the valence electrons flow in the wire like this. So if this is your battery, here's my battery, it looks like this. Well, I'll just use one electric cell because it's too hard to hold. And if I put this right here and this right here, you can see that it's glowing. Now this is the negative side of the battery. So what happens is that because it's a closed circuit, that is, I have a closed loop for them to travel, the electrons are forcing themselves to move through here. And then they go in here and then they lose energy, give off energy as light, and then they move through in here and they get sucked in. Okay? And then the battery forces them to flow again. So they go in loops. Okay? So this flow of charge in a wire, we have a name for the flow of charge in a wire. Anybody know what it is? I'm sure you've heard of it. Well, electricity, yeah. But I think, current, electric current. Have you heard of the word current before? An electric current? Sure. And that's what's happening here. The charge, there's a net flow of charge. Now, here's a problem, folks. And I'm sorry this happens. What's really happening in this circuit that we just, this right here, which we drew symbolically over here, is that the electrons are flowing this way. But current was defined before we knew what exactly was happening in those wires. Now, by the way, who figured out, or who assigned the positive and negative charge to these different kinds of charges? It was Benjamin Franklin, one of America's founding fathers. And the first great American scientist was Benjamin Franklin. He was a world-class physicist as well as a great statesman and politician and diplomat and so on. And he said, hey, we've got this kind of static electric charge. I'm going to call it positive. And we have this other kind of static electric charge. I'm going to call it negative. He actually thought that something that was positively charged had too much electric fluid, and that something that was negatively charged had a deficit of electric fluid. And so he thought that it was electric fluid. Well, you know what, folks? There's no such thing as electric fluid. There's positive charge and there's negative charge. There's protons and electrons. He didn't know that. Electrons and protons weren't discovered for another 150 years after Franklin. But we've kept with the positive and negative charge. Now, what actually flows in a wire is negative charge, the negative electrons. But we pretend that it's positive charge that actually flows. So really in here, we're going to say that the charge is actually flowing, the positive charge is flowing like this. The current is flowing like this. When in reality, what's actually happening? Electrons are flowing like this. But we're going to pretend that it's positive charge flowing like this. And by the way, positive charge flowing like this gives you exactly the same answer. It works just as well as negative charge doing this. It's fine. It's okay. Now, if only Benjamin Franklin had guessed the other way. He had a 50-50 shot and he blew it. Because if he had just switched, it's called, what ended up being the electrons positive and what ended up being the protons negative, then electricity would be a little bit easier to learn. There wouldn't be this weird pretending of positive charge flowing. But we're stuck with it because all the textbooks define it this way, and we're stuck with it forever. Now, by the way, there's another really interesting example of being stuck with a mistake. Okay, and that is right here. Look at my keyboard here. Let me zoom all the way out. You've heard of the QWERTY keyboard? QWERTY, QWERTY. The QWERTY keyboard. Why do you think the keys on a keyboard are arranged the way they are? How come it's not A, B, C, D, E, F, G or anything like, why is it like that? No. Well, sort of, yes. Here's what happened. The typewriter was invented around 150, 160 years ago, early 1800s, mid 1800s. The first typewriters. Before that, everything was handwritten or they had set type in a printer. But then they started inventing the typewriter, and they were very clunky. And if you tried to type too fast, the keys would jam up and get stuck. And so what they did was they arranged the keys on the keyboard to be as inefficient and slow as possible so that when typists learned where all the keys were, they wouldn't jam up. So the QWERTY keyboard is the worst possible arrangement of letters you can get to slow down a typist. Well, now we have these electrical devices, these laptops. Yes, there are other arrangements of keyboards that are much more efficient. Where the letters you use the most, you use your these two fingers, and then the letters you hardly ever use will be for your pinky or your ring finger. Well, but you know what? No one uses them. Why? Because we're stuck with the QWERTY keyboard. Because all the keyboarding teachers, they know how to use the QWERTY keyboard. I guarantee you, your great-grandchildren will use the QWERTY keyboard. We're stuck with it forever. Unless civilization falls and then rebuilds itself from nothing, we're going to be using the QWERTY keyboard. Okay? And the same thing is true with charge. We're stuck with the negative charge on the electron, but we're also stuck with the definition that current is the flow of positive charge. Okay, now, let's get back. So what is charge? Charge is a collection of either protons or electrons. Okay, now, what variable do we use for charge? We use the capital letter Q to represent charge. I'm sorry, I know we use Q for heat, but we also use it to represent charge. So you have to look at the context. If it's an electricity problem and you see a capital Q, it's charge. If you see a heat transfer problem and it's capital Q, that means heat. All right, so Q. Now, what units do we use for charge? Think of a gigantic basket full of electrons or full of protons. We use coulombs. A coulomb is a quantity of charge. It's a whole lot of electrons. One of the homework problems is to figure out how many electrons are in a coulomb of charge. Here's what you need to know. 1 electron is equal to negative 1.6 times 10 to the negative 19 coulombs, a ridiculously tiny number. So a coulomb of charge is a lot of charge, actually. Now, so we measure, yes? Yes. It won't fit on the paper now because I drew it too wide, but there we go. A coulomb of charge is just a big collection of trillions and trillions of, thousands of trillions of electrons, or thousands of trillions of protons. By the way, 1 proton has a charge of positive 1.6 times 10 to the negative 19 coulombs. Oh, we use a capital C to represent coulombs. Now, current. Current is the flow of charge. Okay, it's how much, it's the amount of charge that passes by per unit time. Now, current, by definition, is the amount of charge that goes by in a given period of time. Charge per unit time. Now let's write it as an equation. What letter do we use to represent current? I don't know why they pick these letters. I'm sorry that they do. It makes it confusing. I. You just have to memorize it. The capital letter I, if you're dealing with electricity, capital I almost always represents current. Some books use lowercase I. We're going to use capital I. Is equal to the change in charge, the amount of charge that goes by over a change in time. Now let's take a look at that in terms of units. That's coulombs per second, yes? And we have a name for a coulomb per second, an amount of charge that goes by per unit time. A coulomb per second is called an amp. Well, technically an ampere, but nobody calls them amperes, except maybe the French. We call them amps. Now, have you heard of that term amp? How many amps does that thing have? Like your hair blow dryer might pull an amp. I have an electric weed whacker. It uses 5 amps. 5 coulombs of charge moves through the motor every second. That's a lot. 5 amps. Now, what's the abbreviation for an amp? Capital A. Makes sense. So these are, this is the equation for current. These are the units. Q is coulombs per second. A coulomb per second is called an amp. Now, if I look at my circuit over here, well, I've got electrons flowing down this way, but what we do is we pretend that it's positive charge flowing this way. So the current is actually flowing up the wire. And here's how you can tell. If you have a battery like this, see this battery? See the plus sign right there? That means the current that it tries to make is going to push this way. going to go to the left, and it's going to go this way and up, and then it's going to pull it in. Now, in reality, what's actually happening? Electrons are flowing the other way, but we pretend that it's positive charge going that way. And if you don't blame me, blame Benjamin Franklin. And getting mad at Benjamin Franklin is downright unpatriotic, okay? Okay, so now we're going to talk about the circuit in terms of energy. Now, batteries, as you can see here, when I hook up the battery here to a light bulb, it gives off energy. The light bulb is giving off energy, and the supply of that energy is the battery. How much energy is in a battery? Well, we don't really measure it in joules. We use joules, but we don't really measure it in joules. You've probably heard of this quantity called voltage, right? Volts. And if you look really carefully, where is it? It's right here. It's upside down. You can. I don't think you can read it there. If you get on YouTube, you might be able to read it. But right here, let's zoom in as much as we can. Let's zoom in. Oh, there we go. Let's let it adjust. Oh, this is terrible. Come on, hurry up. Oh yeah, you can see it. See right there? This thing's like a microscope. 1.5 V. What do you think the V stands for? Volts. Volts. Here's your measure of energy in a battery. Voltage. But what does a volt mean? Let's talk about voltage. Okay, oops, I gotta zoom out. Okay, voltage is a measure of energy per unit charge. So when this battery, we say this, or this electric cell, I should say, has a change in voltage of 1.5 volts. Now, by the way, voltage is one of the few quantities that I know of, I think it's the only one I know of, where the variable and the unit are the same letter, capital V. So it's kind of nice. 1.5 volts. What does that mean? Okay, here's what it means. 1.5 joules of energy for every coulomb of charge that it delivers to the circuit. So here's my electric cell. It has a voltage of 1.5 joules per coulomb. That means if 1 coulomb of charge moves through it, it delivers 1.5 joules of energy to the circuit. Now that energy is stored in the molecules in here. It's electrochemistry. Okay, but now what would be the change in voltage if I put in 2 batteries? Or 2 cells to make a battery? Well, this one's delivering 1.5 joules per coulomb, and this is delivering 1.5 joules per coulomb. So what's the voltage here? 3 volts. 3 volts. Now, the robot that our robotics team makes has a battery of 12 volts, and your car does too, 12 volt battery. That means for every coulomb of charge that flows through your wire, it delivers 12 joules of energy. Okay, so a battery, see, this is a voltage source. This is energy in. Energy enters the circuit. What does a resistor do? Well, a resistor, like a light bulb, for example, energy comes out of the circuit as light or as work or as heat. It does something to the environment. So through a resistor, energy out. Energy in, energy out. Energy in through the battery, energy out through the resistor. Now, in a circuit, you've got to have just as much energy coming in as energy coming out. That's conservation of energy. Okay, so you got energy going into the circuit. You've got to have just as much energy coming out of the circuit. Now, how do you figure out how much energy is in the circuit? Okay, and let me do this one thing, and then we'll take a little break. And here we're going to talk about power. Power. The battery delivered, let's say our battery delivers a certain amount of, it has a certain voltage. That is, it delivers a certain amount of energy per unit charge that flows through it. So P is for power. We learned that before. And we've got a certain amount of current flowing, I. Now that's coulombs per second. This is a measure of how much energy, how much charge is moving through our circuit every second. And then we have voltage. This is, V is how much energy the current is carrying and delivering per coulomb of charge. Watch what happens when I multiply them together. And you'll see that it is power. Here's current, but current is coulombs per second, isn't it? I'm just going to put the units in parentheses. Well, what is a coulomb per second? It's an amp. Amp is a coulomb per second. Times voltage. Well, what is voltage? It's a joule per coulomb. Well, what happens when I multiply a coulomb per second times a joule per coulomb? What do I get? The coulombs cancel. I get a joule per second. That's how much energy I'm delivering to the circuit every second. So this is the power, and that's in watts, right? A joule per second is a watt. So P equals I times V. If you know the current through your circuit and the voltage that your battery is delivering, then you can figure out how much power is coming out. Now let's go back to my circuit right here. Oh man, this piece of paper's really gotten crazy. Here's my battery. When I go, the electricity over here, we're going to say the electricity doesn't have any energy yet, but it's marching through, and then it goes through the battery. Boom! It gets lifted up in energy per unit charge. Let's say 3 volts. Boom, I've got 3 volts. That means I got 3 joules of energy per coulomb of charge. Then I get to the resistor. Now what happens at the resistor? That energy gets delivered to the world. It gets removed from the circuit. In this case, in our example, it gives off light and heat. And then or if you hook it up to a motor, it can spin, it can do work. And then it's back to where it started. So the voltage gain, the increase in energy per unit charge is equal to the voltage loss through the resistor to get back to where I started, and then it just goes over and over and over again. Okay. So let's do a quick, let me zoom all the way out and do just a real quick review. Matter is made out of protons, neutrons, and electrons. Neutrons don't have any charge, but protons have a positive charge. They push other protons away. Electrons we assign the negative charge to. They push themselves away. But electrons and protons are attracted to each other with force. And when you apply a force through a distance, you can do work. And when you do work, you can transfer energy. In a circuit, which is a closed path, you have a battery that has energy in it. It delivers it to the charge. Then that charge jumps across the light bulb and releases its energy. And then it flows back to where it started to pick up more energy from the light bulbs. Now what's really flowing as a current in a wire is negative charge, but we pretend that it's positive charge moving the other way. Thank you, Benjamin Franklin. Okay. Now charge, we use the letter Q to represent how much charge there is. And we measure it in coulombs. One electron or one proton is 1.6 times 10 to the negative 19 coulombs. It's a very small amount. Okay. Current is the flow of charge. We define current to be how much charge flows by per unit time. Coulombs per second. Coulombs per second is an amp. So that's current. Now voltage is a measure of how much energy we put into that charge, how much energy it carries per coulomb of charge. So our little electric cell has 1.5 volts. That means it delivers 1.5 joules of energy per coulomb of charge that goes through it. You can also think of it as 1.5 joules of energy per coulomb of charge. It has to drop down if I only have one of them in there. If you multiply current times voltage, you get power. Because a coulomb per second times a joule per coulomb gives you joules per second. So there's your equation for power. Okay. Now, we're going to take a little break. And when we're done with the little break, we're going to talk about Coulomb's law. Not Coulomb's law, Ohm's law. But I want you to take a little break before we get to Ohm's law.